So hello everyone again and welcome to my channel. So here we're going to continue from where we stopped on our previous video, where we looked at Lewis diagrams and most importantly how we can construct compounds related to Lewis structures. Now Lewis structures is some kind of representation of these particular compounds when writing it in paper. So one thing you need to note about Lewis structures are: one, you need to know that for the representation of the valence electrons, you represent them as just, or it as just one dot, and this one dot just represents one electron. On the other hand, if you're looking at bonding pairs of electrons, then you need to take into consideration that you're looking at two electrons involved in here. As a result of that, these two electrons could either be written as this, or it can be written as dash, which represents the connection between two atoms by just a bonding pair of electrons over here. So all these arrangements of atoms has to be done in appropriate noble gas configuration. So if you're looking at, let's say for an atom here, let's say for example carbon as usual has 4 valence electrons. If you want to make it to become some kind of an octet atom, you need to be able to add 2 more electrons by sharing the electrons in order for you to gain a configuration that is related to the noble gas configuration. So let's take for an example. We have methane. Methane is an interesting compound, pretty much a gas, and it has a molecular formula of CH4. Now CH4 implies that C here is the most electronegative atom, so it should be at the center. And what happens then is that it needs to be able to distribute the electrons in a proper manner enough for it to have a stable octet. We know that hydrogen has 1 electron. Since you have 4 hydrogens, then what happens is that you introduce 4 electrons, and carbon has 4 valence electrons. 4 valence electrons. The total valence electrons in this whole molecular formula is 8 electrons. And now this total electrons of 8 must be distributed in this particular carbon. So you put them in pairs: 1, 2, 3, 4, 5, 6, 7, 8. Now you position the hydrogens around it: 1, 2, 3, 4. So in this case here, we realize that carbon, which has 4 electrons, once it's in this particular molecule, is going to gain an octet configuration, which is similar to its closest noble gas, which is neon, enough for it to become more stable. And hydrogen will have 2 electrons here by the sharing with carbon, enough for it to have a stable octet, or I would say a configuration similar to its closest noble gas, helium. So next we have, but anyways, before I forget, this is how methane looks like. Interesting tetrahedral structure over here. So in here you have carbon, and the surrounding are hydrogen atoms. Quite interesting that the symmetry is not as in proportion as you would like it to be, like a cross. It's kind of interesting. Why? Is because you have some kind of a change in the overlap of the orbitals that we'll be discussing in our future videos. Anyways, next we have ethane. And ethane has a molecular formula of C2H6. C2H6, now we know that carbon has 4 electrons, since you have 2 carbons, 4 plus 4, 8 electrons for carbon, and hydrogen, we have 6 hydrogens. Each hydrogen has 1 electron. 6 times 1, 6 electrons. Now 8 plus 6 gives us a total of 14 electrons that are valence, and this valence electrons needs to be shared in all this particular molecule over here. So as a result of that, carbon, which is over here, we have 2. Now we need to distribute these 2 electrons in total 14 surrounding this particular carbon to complete its octet. So what we have here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the last 2, we need 2 more, so to generate 2 more for these 2 to be stable, they need to share 2 electrons, forming a bonding pair. But you will see it in close proximity as you include the hydrogens. So in here, the carbons, they are octet configuration stable. Now if we include hydrogen to the other bonding pairs, then you get a nice configuration that's of this particular manner with respect to the Lewis structure. Now if we proceed further by introducing the dashes to reveal the bonding pairs, then what you realize is that you have a dash between the carbon atoms, and then you have hydrogen, 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 hydrogen. So this over here is the molecular structure of ethane, and that is about it for ethane over here. So if you look at the molecular model, we see over here that this is like a methane and this is another methane, right? But now if I remove this hydrogen over here and I remove this hydrogen over here, right, what I have is 1 electron on this carbon, and I have 1 other electron on this particular carbon. If I fuse those 2 electrons together, what I get is ethane, where I have hydrogen, hydrogen, hydrogen here, hydrogen there, hydrogen there, hydrogen here, and in here we have a bonding pair between the 2 carbons over here. So quite impressive, you're seeing everything in 3D over here. And it's quite interesting that you have 2 forms. You have the eclipse, which is in this nature, and we have the staggered, which is of this nature over here. But anyways, all these are just relative isomers that you'll be focused on later on in this particular channel, but that's about it for ethane over here. So let's look at the non-bonding electrons system in a particle molecule. So non-bonding electrons are mostly electrons that are not shared between 2 atoms. So in this case, what we need to call them now, we call them lone pairs in this case. So once we consider them to be lone pairs, what they are known to be is that they're not involved in any form of bonding. So that is why we call them non-bonding electrons in this case, and they are kind of similar to that of removing a hydrogen off here without its electron moving out. So as a result, we have 2 electrons sitting on carbon, but that you're creating a charge, but that is just a similar case in this particular situation over here. So as a result over here, we know that most atoms that are present in molecules that exhibit these lone pairs are mostly oxygen and halogen atoms. So all these atoms, if you have them in a molecule, the chances of the presence of lone pair in that particular molecule is much more higher when you have oxygen and helium atoms compared to other atoms, like for example phosphorus, probably phosphorus, yeah, or sometimes any other element in periodic table, or nitrogen as well. Sometimes nitrogen does have lone pairs, sometimes it doesn't. But examples include methylamine, so methylamine in this case will have a lone pair on nitrogen enough for it to become stable in its configuration. And next we have is ethanol. Can be used as a solvent in any chemical reaction. So in here, let me put a dash here, or this is not hydrogen, this is a dash, which is a bonding paired to a hydrogen. So in this case here we have two lone pairs, and finally if you're including a halogen, either fluorine or chlorine or iodine, we have attached to Cl, which is chloromethane. This is also a solvent as well. Chloromethane. In here we have ethanol, and lastly we have methylamine. So in chloromethane we have three lone pairs or three non-bonding electrons surrounding chlorine enough for it to obey its octet. So in here we have 1, 2, 3, 4, 5, 6, 7, 8. So the one bonding pair is being shared between the chlorine and carbon. This for oxygen, we have a bonding pair between oxygen and hydrogen, and we have a bonding pair between oxygen and carbon as well. But in here we have two lone pairs on the oxygen, and lastly we have three bonding pairs, two between nitrogen and hydrogen and the other between nitrogen and carbon, and lastly we have one lone pair sitting on nitrogen. But anyways, that's about it for this particular section on Lewis structures. I hope you enjoyed the examples I gave. I'll be posting a video related to more structures involved in developing Lewis structures for compounds, so that you'll be able to be familiar with the distribution of electrons within molecules overall. And I'll be putting it on my playlist called Problem Solving. Overall, thanks again for watching, and please don't forget to hit the like button, share and subscribe. Have a good day guys. Peace. Love you all. Bye.